Another reason more interesting just generally scientifically, is, as I mentioned earlier, just above the thermosphere and in the thermosphere, which is the upper atmosphere, remember, this is where atmospheric escape occurs. And so if we're interested in understanding, for example, life, how did life originate, one of the conditions for life, as we understand it, is that you need liquid water somewhere, at the surface, maybe in the subsurface. And you also need life to not be exposed to too harmful radiation. So atmosphere plays a very important role in protecting life from harmful radiation. And also, liquid water itself can only be liquid in certain temperature and pressure combinations. And so maintaining an atmosphere helps give you the right conditions to maintain liquid water often. Therefore, we think it's important for most forms of life as we understand it. Therefore, if we're interested in looking for life at Mars or at satellites in the solar system or at exoplanets, then we need to understand how atmospheres originate and how they evolve with time. And so this is another reason scientifically why we're particularly interested in studying the upper atmosphere in general and ionospheres in particular. Okay, now there's a few other things from this diagram that I haven't gone into yet. So one, you might notice that there's something around 100 kilometers called the Kármán line. So the Kármán line is a region that, it's a very rough area that separates atmosphere from space. So, in fact, the upper atmosphere, as many people might think of it, is really space. So the Kármán line comes from a definition where you compare the speed of an airplane versus a spacecraft. So an airplane generates lift based on the speed that it's traveling and the density of the air. Okay? And so airplanes at lower altitude have a much denser air, and so they don't need to travel as fast to generate enough lift to fly. But as you go up in altitude, airplanes need to travel faster to generate the same amount of lift. This continues as you go up and up and up in altitude until eventually, to generate the amount of lift that you need to keep an airplane aloft due to the lift, you need to be traveling at the same speed as you would be traveling if you were just orbiting the planet altogether. And so orbital speed is what spacecrafts would orbit at. In other words, it's independent of the atmosphere. And so, very roughly, the Kármán line is the boundary between where an airplane would need to be traveling so fast that it could essentially be a spaceplane or a spacecraft, because it's traveling at the same speed as orbital speed. It also means that above 100 kilometers or so, the atmosphere is so tenuous, so thin, that it does look dark. It looks black if you put a camera up there and look out through the atmosphere. At most wavelengths, it would look dark like space. However, for all the reasons I just described, there are still a lot of important physical processes that happen in this region of the atmosphere. And so it is very distinct from the true vacuum of space, which is above the exobase and outside of the collisional regions of an atmosphere. So one more point that's worth addressing here in this slide is that this is illustrating different atmospheric regions at Earth, and it's using altitude to do that. These atmospheric regions, by and large, are the same regions you would find at other planets, except they would work on a pressure scale instead of an altitude scale. And in fact, most of the similar processes that I've described happen in similar ways at other planets too. And so it's useful to compare what we know about Earth with what we know about other planets. And to do comparative analyses there, we learn more both about the other planets and sometimes more about Earth as well. Okay? So all of these processes will, in general, apply, at least qualitatively, at the other planets as well. The atmosphere, as I've already mentioned, is useful for life as we know it because it filters out harmful radiation from the sun and from just space in general, energetic particles from space. So that's both a benefit and a detriment. The detriment is that means if we're on Earth and we want to observe phenomenon outside of our atmosphere, then it's difficult to do at certain wavelengths. So this plot here shows the atmospheric opacity versus wavelength. So 100% opacity means that the atmosphere is opaque at this wavelength, meaning we cannot see through the atmosphere at that wavelength. Okay? You can see when you get to the rainbow region of the spectrum, that's the visible region of the spectrum, those photons mostly go through the atmosphere, as we know, because we can see the sun at the visible wavelengths of light. You can also see there's a bit of structure as you go to higher wavelength from visible wavelengths. The first wavelengths you encounter are the infrared. Some of the infrared wavelengths go almost all the way to the surface of the Earth, but not quite. Others are absorbed higher in the atmosphere, and so we can't use ground-based observing to monitor those wavelengths, for example. Then, as you go to longer and longer wavelength, you move from the infrared to the submillimeter and ultimately the radio frequencies. And radio, remember, is where some portions of the radio spectrum will be absorbed or reflected by the ionosphere, whereas other radio waves can go through the ionosphere, although they are still affected by the ionosphere and they might disrupt communication of GPS satellites, for example. Okay? So this gives us an idea of why, for example, if we want to study UV photons or gamma rays, we need to use spacecraft because they need to be above our atmosphere to actually monitor those wavelengths. Those photons would otherwise be absorbed by the atmosphere. We can use ground-based telescopes to observe the visible phenomenon throughout the universe. And we can use ground-based telescopes high on mountaintops to observe some infrared phenomenon. Now let's get back to why do we care? For any scientific inquiry, there are many different avenues you can take into understanding why you might care about doing this. A very basic one is that does it directly benefit humanity in some way? Another one, in this case, is you're just interested in what's called magnetospheric science in general. So a planet like the Earth, which has an intrinsic magnetic field, so you've used a compass before probably, and so you know that the compass reacts to the Earth's magnetic field and in such a way that so you can find magnetic north, for instance, and so you can find directions around the planet. A magnetic field in general it looks sort of like a dipole, and this interacts with the phenomenon called the solar wind that I described earlier. So the solar wind is just a constant stream of plasma and embedded magnetic field coming out from the sun at hundreds of kilometers per second. This stream isn't constant. Sometimes it's more dense. Sometimes there's an explosion of material that continues to promulgate outward until it impacts, for example, the Earth. And the barrier between the solar wind and our atmosphere at Earth is the Earth's magnetic field, which forms a boundary called the magnetosphere. And so the solar wind first impacts the magnetosphere and generally goes around the magnetosphere, meaning the magnetosphere, which derives from the Earth's intrinsic magnetic field, protects us from much of the radiation from the solar wind. So one way to think about this is that if you've seen just a rock in a stream, as the river comes through near the rock, the water has to divert around the rock. Okay? So the solar wind is analogous to the water in the stream, and our magnetosphere is analogous to the rock. The main difference where this analogy breaks down is that our magnetosphere is not fixed like a rock would be. It's kind of spongy. And so if the solar wind gets stronger, our magnetosphere might depress. If it gets weaker, it might become enlarged, and so on. Okay? So that's a whole branch of science, which is the interaction of the sun and the solar wind with the Earth environment protected by the magnetosphere. That is called magnetospheric science in general. If you're interested in magnetospheric science, you might be interested in ionospheres as well. Or, I've highlighted just a few more here. We can go into just a little bit of detail. You might be interested in exoplanets. So planets at star systems outside of our own solar system. We've discovered over 3,000 of these so far. People are often interested in exoplanets because it gives us some insight into how our own solar system formed. And for example, there might be habitable planets outside of our solar system. There might even be life on some of these planets. And that's an exciting topic to think about. If you're interested in studying exoplanets, Well, the best example of most of the exoplanets that we've discovered is a Jupiter-like exoplanet. So many of them are so-called hot Jupiters. So they're bigger and hotter, but broadly consistent with what we understand Jupiter to be. Therefore, if you study Jupiter's or Saturn's atmosphere or ionosphere, then you might learn something about how these exoplanet atmospheres work as well. Finally, if you care about solar system evolution, you might be interested in studying an upper atmosphere or Saturn's ionosphere in this case, because one example is that the evolution of the solar system is still, to large degrees, not perfectly understood. One of the ways we don't understand that is, for instance, how did Saturn's rings form? We think they formed in a somewhat analogous way to how the solar system itself formed, which is there was a ball of gas that was rotating. As it was rotating, angular momentum sort of spread that ball out into more of a disk shape. And then within that disk, little clumps of density started forming planetesimals. Those planetesimals started accreting more matter until you have essentially planets. There's a lot of other physics buried in there, but that's the basic of the explanation. We think planetary ring systems, like at Saturn, may have formed in a similar way. But we don't really know at present. And so we might want to study more about planetary rings and their interaction and evolution with the space environment. In particular at Saturn, we think that Saturn's rings have been shaped by their interaction with the magnetic field of Saturn and the atmosphere of Saturn. So the rings have been losing mass to the atmosphere over time. And so if we can monitor that rate of mass loss, then we can learn more about the evolution and lifetime of Saturn's rings. Finally, you might just want to study an upper atmosphere or Saturn's ionosphere because it's cool. And honestly, that's the answer for a lot of scientists. They don't need to go much further than that.